Have you ever just looked around? I mean, really looked? Everything you see, the chair you're sitting on, the screen you're watching this on, it's all the result of a silent, invisible conversation. A debate, really, between different materials. So today, we're going to learn the secret language engineers use to decide what gets made out of what.
It's a question you might have asked yourself. Why is that? Why can't we just build a plane out of steel? Or maybe a bridge out of aluminum? Well, the choices behind these incredible structures are definitely not just about what's cheap or what's easy.
No, it's totally deliberate. It's a language, spoken by engineers and scientists. Every single material has its own unique set of characteristics, its own vocabulary. And choosing the right one means finding the perfect word to solve a very specific problem.
Okay, so how do you get fluent in this language? Well, it all starts with what we're calling the material question. And the answer is always found in a material's most basic, fundamental properties. Think of physical properties like a material's resume. Seriously, they're the hard data, the measurable, predictable stats that tell an engineer exactly how that material is going to perform when you put it under pressure, or heat it up, or put it under stress.
So let's dive in. We'll start with two of the biggest puzzles in all of engineering: how you manage weight and how you control temperature. This right here, this is the classic aerospace dilemma. You need something unbelievably strong to handle the forces of flight, but every single ounce you add makes it harder to get off the ground and costs more fuel to keep it up there.
And the answer? It comes down to one single property: density. It's a pretty simple idea, right? It's just how much stuff is packed into a certain amount of space. But for an engineer, lower density means less weight. And that changes everything.
And right there, you can see the fundamental trade-off engineers are always dealing with. Aluminum has this amazing low density, which is a miracle for airplanes and cars where every single gram matters. But for a giant bridge, well, you can go with stronger, denser steel and just design the structure to handle its own weight. It's this constant balancing act.
And the cool thing is, you can figure this out with a beautifully simple formula. Density equals mass divided by volume. That's it.
So if an engineer has a little sample of some new material, and they know its mass and its volume, they just pop those numbers right into the formula.
And boom. In this case, they get 0.25 grams per cubic centimeter. That one little number, it tells them everything. Suddenly, they can compare this material to thousands of others. It's a simple calculation that can literally make or break a billion-dollar project.
All right, so let's shift gears from the challenge of weight to the challenge of temperature. This is a problem we all think about every single day, whether you're grabbing a thermos or just hoping your house stays warm. The goal is always the same: you've got to control the flow of heat.
And the property that's in charge of all this is called thermal conductivity. It's basically just a measure of how quickly a material lets heat pass right through it. Imagine it's a highway for heat, right? Materials with high conductivity, like metals, they're like a superhighway. Heat just zips right through. That's perfect for something like a heat sink in your computer that needs to get rid of heat fast. But low conductivity materials? They're like a slow, bumpy country road. Heat barely moves at all, which is exactly what you want for your coffee thermos.
Okay, so we've got weight and heat covered, but what about just, surviving out in the real world? Materials are constantly being attacked by their environment.
Rust. It's the slow, relentless enemy of so many things we build. This chemical attack can weaken and eventually just destroy even the strongest metals. So how do engineers fight back?
Well, they do it by choosing materials with high corrosion resistance. This is like a material's built-in defense system against attacks from moisture, salt, air, you name it. And engineers have basically two ways to tackle this. They can pick a material that is intrinsically resistant, like stainless steel. It's got protection baked right into its chemistry. Or they can take a more vulnerable material and give it a suit of armor, like a layer of paint or a powder coating, to shield it from the outside world.
Now, a material might be perfect on paper, right? Perfect density, great corrosion resistance, but if you can't actually shape it into what you need, it's completely useless. And this brings us to the properties of fabrication. These are the how do we actually build it questions. Can you join two pieces together? That's its weldability. Can you make it tougher and more durable, like for a tool or a gear? That's its hardenability. And can you melt it down to pour it into a complex shape, like an engine block? Well, that's all about its melting point. Without these, even the best material is just a useless lump. All right, but it's not all about brute strength and heat. Some of the most critical properties are totally invisible. They deal with the hidden forces of electricity and magnetism.
This is where we get into the stuff that powers your phone, your computer, everything. Permittivity, which is how well a material can store electrical energy, that's the magic behind capacitors. And its magnetic cousin, permeability, that governs how a material reacts to a magnetic field, which is the key to everything from electric motors to electromagnets. I mean, our entire digital world is built on these two properties.
And listen, we have barely even scratched the surface here. There are dozens of other properties that engineers are constantly thinking about. Things like thermal expansion, how much something grows or shrinks with temperature, or recyclability, which is becoming more and more vital for a sustainable future. Every single one is another word in this incredible language of materials.
So every single object you see is a result of this long, complicated conversation. But our needs are always changing, right? As we look to the future, to building lighter cars, more efficient computers, and sustainable cities, you have to ask yourself, what new words are we going to need to add to this language? What will the materials of tomorrow need to do?